the client didn't want to have a wind speed sensor. So since we didn't have a wind speed sensor, we were looking around for what we could do. And we found possibly as a corner case in the desert, wind speed was highly correlated with time of day and fairly consistent. So at sunrise and sunset, then the winds would pick up. And so then we could get a typical wind speed by time of day, and then use a model to come up with a prediction. So that ended up working out fairly well. If you were in Central America in a jungle area, that might not work out at all. But that was something for this case. For the general application, we would be assuming to have a wind speed sensor. So go ahead and continue.
Yeah. The first part is basically the mask segmentation model. So if you don't know, in ML, we have computer vision. In computer vision, we have multiple kinds of problem. This one is particularly called mask segmentation problem, that given an image, can we exactly segregate object of interest. Like for in this example, we are detecting where actually the flare is, and the second where exactly the smoke is. By this, we can exactly map the area, and we can map the volume also by a conversion factor. And we have this.
Your voice is getting lower again, Himanshu. Try and speak louder or closer.
Okay. Yeah. So the first task we worked on this training this model, which can tell us where the fire and smoke is in the image. Now I will discuss. So this mask-based RCNN, there are multiple approaches that we have for mask RCNN. It's a very evolving field of computer vision. But the one model that we used was Facebook Detectron. Basically, the crust of the model is it's used a fast as a backbone. And what advancement it has done is basically, other than a class box, which class the object belongs to, it also has a convolution leg for that converts for an image. It converts it to a mask. Like here in the image, it is exact telling where the person are, and it convert from image to image conversion. Yeah, and other than that, it also gives us the class boundary boxes. The reason for choosing this model is basically we are an edge-based computing company, and we have to run this model in a very constrained environment, which is resource deprived. Like we don't have that much of resources available in terms of computation, and also the environment that we had in the machine was very given. Like we can't modify much of the environment. There is some other models that are available in the research that are higher than this one, but they required some higher computation. But for example, efficient that is one of the highest rated model in terms of mask model, but that required a TF2. At that time, they didn't support it, so that's why we used the Facebook implementation of the mask RCNN, which is also pretty good. Like in terms of accuracy, in terms of precision, it is very close to this one. But efficient that is of SOTA category in this one. And also Facebook Detectron is implemented in PyTorch. We use the Matterport implementation of same model that was implemented in TensorFlow and Keras. So I just listed some of the models there in terms of mask model. So if you see papers with code ranking for semantic segmentation, efficient net, deep lab version 3, these are some of the sort of papers, and we have worked on them, but somehow or another we face a blocker, and we finally decided to go with this one, ResNet 101 based Detectron model, which was implemented in the PyTorch and this one. One thing to mention here is that getting label data for this particular problem is very costly and time consuming. Because from the labeler side, they have to label exactly the mask of, it's not a bounding box where you just draw simple. It has to be pixel by pixel accuracy that the person has to draw where exactly the object is. Yeah, as Greg suggested, we have also taken help from some 3D image generator, Paracosma. What they had a engine that can, given a scenario, they can generate white background images for us. And yeah, labeling is also not needed for them because they have all the control environment. They can tell what object is where. That was really helpful in this. Now, why we wanted to use a mask model for this particular approach is that I wanted to discuss. First, we could have simply gone with a object detection model, which detect like the bounding fire is in the bounding box, and we can tell the length of the fire. The problem is, let's say if this is the fire and we are saying this is the bounding box, of course, the bounding box would be calculating the length of the fire as this one, while the model, the physics-based model that we required, required as an input would be the curvature length of the fire that's going. This is a simple case where the fire is relatively vertical, but there could be a case where the fire is bent like this. It's a nearly horizontal when the wind is blowing faster than the velocity the air is coming out. So mask model is particularly helpful in that case, that we can, when we have a mask, we can travel around the centroid of the mask, and we can calculate exactly uh, the length of the curvature length of the fire, and that would be helpful as an input for our further physics based model. I will also show you like how much sensitive our model is based for this fire length. As Greg mentioned, it is particularly sensitive to pixel mapping, but for the flare length also it is very sensitive. Like if there is an error of 10% in the flare length, it is a factor of 2 times. Like it would be 20% error prone in the final output. Secondly, the 3D estimation that we do from a 2D figure is much more accurate than a bounding box. We have like one estimation model which converts this 2D mask to a 3D volume sphere. So for that, the bounding box was not appropriate. We use this mask to convert this. You can imagine this as this is a cone, and we imagine it in a 3D scenario where we revolve it around its axis, like we rotate it around its axis. Now we imagine a cone around this, and we have a spherical volume calculated around this, and we integrate, and we calculate the overall volume of the flare that's there. It of course makes the assumption that the fire is circular at a particular cross-section, but according to our analysis, it was very fair to assume, because this is a controlled flow environment where the fire is designed to be in flow manner. Yeah, so this was the final result. The model that we developed was based on the mask RCNN. We have also implemented or trained some other efficient DET model, D4, D6 model. They were resource intensive, of course. And the mobile net, which was the lighter one, and required 224 by 224 image, was cheapest in terms of taking computation, but it was not very precise and accurate. The masked RCNN model was, as you can see, in some category in the flare precision, it was greater than efficient DET model, but in some of the categories, it was not that well. Like in the smoke precision category, masked RCNN model is not that good. Efficient DET D4 performs better than the masked RCNN model. One thing to note here is that the camera which we are working is a very standard environment. It's not like we are deploying in a wide variety of background. But the image that we taken out was taken some from internet, some from Paracosma, which was 3D generated, which had wide variety of background. That's why these number could be not that significant in terms of when we deploy it on site, the accuracy would be much higher than these reported numbers. But in a general scenario, this is the reported accuracy from our model. As you can see, it's performing pretty well. We have tested in a wide variety of background, and it works pretty well in terms of accuracy and predicting where the fire is. Yeah, coming to the part 2 of the physics model. So what we have covered till now is we have a video stream coming in. We feed it to the MRCN model. It gives us this flare mask and smoke mask. Based on these smoke masks, we do a basic calculation over like what is the conversion ratio, like how much one pixel is depicting in terms of feet and length terms. And based on that, we calculate these 9-10 parameters that we have. And out of these parameters, one crucial parameter that I discussed is the fire length. Fire length, again, just to reiterate, the fire length is basically the length of the fire that is calculated from the stack tip, the center of the stack, till the end of the stack, the curvature length that's going along the fire. So that's taken as an input of this physics model and wind speed prediction. So there is a empirical based evidence that's available like from research. They have calculated this in a controlled environment that if the behavior of the stack is very predictable in that like how much of the fire length we would observe if we are giving this much of flow. These stacks are designed to be behaving in a certain and we can exploit that configuration to basically predict how much of the volume we are burning. These stacks comes in four kind of configuration, and we have basically collected empirical evidence for all these four configurations. The HP here stands for high pressure stack, LP stands for low pressure, HT stands for high temperature, LT stands for low temperature. As someone mentioned, the Venturi effect, I think that is related to the high pressure condition. So in that case, the flow rate, if you observe, won't be that high. If the pressure is very high in the stack, and in that case, we don't, the stack is designed in such a way that the fire length should not go above a certain threshold. That's a stack configuration parameter. And the ask from the client is that fire should not go out of the frame from the stack itself, from the camera view, sorry. So in the Venturi effect, so that could be avoided in this case. Yeah, and the third part of this particular model is wind prediction model. So the wind prediction sensors are very easy to come by. They had allotment sensor at the site and talk with them. But the thing is, our system.
Can you try and maybe go back to your headset or something, because the volume is still going up and down on your microphone, and it's really hard. I don't know what the problem was with the audio.
Can you give me 1 minute?
Yeah, Greg, is it better now?
Much better, yes.
Okay. Yeah, as we're discussing, the third part is the wind speed prediction model. The real-time sensor that they had at the site was not particularly integratable with our system. But given that our model, this physics-based equation, require the wind speed as a first input as a crucial parameter, because the banding of the fire is directly dependent on how much is the wind speed blowing. We required this particular parameter. So we came up with some analysis. Like the first analysis that we did is that wind speed at the site was very cyclical. In that terms, it goes high at the particular time of the day and then it travel down. Yeah, we had only 3 months of data. Based on that, we did this analysis. And what we also seen that the angle of the fire is also correlated with the wind speed, that higher the wind speed, higher, lower would be the angle from the horizontal. So we came up with a simple polynomial regression based model based on these two parameters, that the wind speed is cyclical. It depends on the time of the day. And second thing, it depends on, or I would say it's a direct correlation with the angle of the fire. We feed these two parameters as an input to the polynomial regression model. Yeah, we also predict wind speed from the KPI that we calculate. In terms of effect of wind speed that we observed, so this is the normal prediction model. At the speed of 8 meter per second, this would be the flow rate predicted. But if the wind speed is lesser than that, we have a 1% error or 1 meter per second error in the calculation, then the predicted flow rate uh, would be far away from actual one. What we have observed is if the flame length is very high, then the effect become more visible. Like in terms of error, the flow rate would be much higher or lower than the actual one. But when the flame length is lower, which is typically what we had at the site where we were working at the Vasit site, the flame length was not higher than the 60 feet range as far we have observed. So from our calculation, we have seen that maximum the error that our wind speed prediction model was giving was 0.1 million cubic feet per hour, which is a reasonable estimate given the client didn't had much accuracy expected from this project. Like they had a limit of 25 to 30%, and this was in well under the limit of 4-5% error that is expected. And our wind speed prediction model was giving accuracy of 1 meter per second, like it had plus minus 1 meter per second, while the range of the wind at the site was plus 1 to 8 meter per second during the time of the day, which is fairly from the feasibility of the project, it was good, because otherwise we would have halted at the initial phase. As I discussed, that wind speed is a basic parameter that the physics-based model require as an input. That's why this was very crucial for us to either get it from the client or to do it by ourselves. So we choose the second way to predict it rather than stopping the project altogether. Yeah, and these are some of the results that we have observed. So as you can see, this is a flow rate flow meter. One thing to note here is the accuracy of this flow meter is per hour. Like it calculate only in the last hour how much of the flow went through it. While our system is a real time, that's why you see more actions or more up and down in the graph. The orange one is predicted from what's happening from visual inferencing. One thing to observe here is that the flow meter is placed at the bottom of the stack, while the visual inferencing is happening at the top of the stack. So there is some latency in the system. In that sense, our system would be detecting a higher flow when the flow meter is detecting it before it is actually happening at the tip of the stack. Yeah, and the accuracy which we have seen, the flow rate which was given by the flow meter at that particular hour or instant was in the range of 20% when the peak flow was happening. This one was for the HP high pressure stack that we have observed. For the low pressure stack, where the flow rate, if you see, is in millions, like I think 1.2 million low pressure stack, we had higher volume in terms of flaring happening. Here also the accuracy and the trend that it was able to predict match quite well with what's happening actually on site. As you can see, this peak is actually happening in hour slightly later than expected. Yeah, this is again another LP stack that we observed, and this was cyclical, and it was able to predict quite well about what's the trend of flow going in and out. This is our real-time dashboard, which basically gives multiple parameters which are of importance to at the site, and this works in multi-stack configuration. Like one camera is deployed, and the client just need to tell where is the stack in the image, and we basically calculate the output flare volume for that particular stack. So these parameters coming for the stack 1, then these are for the stack 2. These are KPIs related to that particular stacks, and these are the overall KPIs that we have computed in addition to all the stacks that we had. Yeah, these are some appendix, I think. Because these came, we have observed this phenomenon, like the stack parameter that are designed are inertia dominated, which is the Venturi effect, like the pressure is going above. This is not a observed phenomenon at the site. Like the stack is typically at the site we had worked on was not like this. The futures, some of the future scope for this project was the predicting the gas composition, because as you see, the gas density is a input to the physics model that we were using, and it depends highly on what is the composition. So as of now, you have to give as an input what is the density of the gas that the stack is working with. But if we had the composition, or we can predict the composition from the flare color, and the smoke coming, smoke also, then we will be able to predict the density of the gas as well. And the second would be integrate the real-time wind sensor to reduce the sensitivity of the model. And then we could also auto detect the stacks for self configurability. As of now, the client has to, in a UI, has to input like there is a stack and there is second stack. We could also integrate this as our model input, that to be able to detect the stacks by itself. Then there are some boundary cases in which, like we have widely exposed images in which we have sun in the background, or we have a light source which is making the camera blurry, or we have wide exposed images that could be gone through auto correction mode in our model itself, and then gone through the model input. That's currently not there. This could be an additional scope for the project. Yeah, I think, yeah, that's it. If we have any question, we can discuss.
So any questions from the audience or anybody? So this is an example of one of about 5 oil and gas enterprise solutions that we've been working on with combining vision and sometimes with physics models, or really whatever is needed to get the job done. And we've rolled out at a number of different sites with these. One of the questions on the chat SR had was, he was asking about the diameter of the pipe where it was being measured at the sensor of the flow meter versus the diameter of the pipe where it comes out at the tip. And if they're different, then they would have a different speed. And I responded on chat, yes, there is a difference there, but they were already close. They weren't that far apart. But that would be a contribution to part of the 10% error. I would call that measurement error. So description of the, somebody, Greg Weinstein asked, description of what the cloud resources were, the computer necessary to train and operate the models. So the training system is one kind of model, one kind of hardware architecture, but to operate the models for inferencing. So that would be like an Intel i7, like a 4-core model. And so then we were running this on that Intel i7, or I mean, it would be 4 physical cores, 8 threads. And so we were running on that. Himanshu, can you speak to what the frames per second was? Was it about 1 or 2 frames a second?
Yeah, this mask RCNN model, we are running at 10 frames per minute. Because we wanted to calculate the real time is for this project is very low, because as of now, as I discussed, the flow meter reading comes out per hour. Like it gives only 1 reading in one hour. So for this one, we ran it as low FPS. And the second thing is the machine on which we ran is a non-AVX machine. It's, I think, 10-year-old system, which is very sluggish. and they are running only one solution at it. And we didn't want it to burden it with much more than it is required. It could, the solution, if given a full potential, it could run at 5 FPS also.
Okay. Okay. And then a question from Yash on the chat. During extremely poor weather conditions, the image fidelity could be poor. I would assume like a sandstorm. The training set may not include a proportionate number of images skewing the distribution. How do you account for these? So I would say, I mean, that was part of the 3D image generation, is that we could try and come up with different use cases and corner cases. And part of what we did do was like a windstorm where there was sand. So we did anticipate that to be something in the future we'd have to inference on. So we put it in the training set. We don't have to worry so much about the distribution. Like, is there 5% of the image is a windstorm or 50% image is a windstorm? We don't have to worry at that level. We just have to have a sufficient volume or variety for the neural net to learn that corner use case. Himanshu, do you have any other comments to add for that question?
Yeah, we have used the Paracosma 3D label also, and we have a very robust augmentation library and internal. So depending on the weather, we have widely observed around Aramco what kind of weather condition we have. So for that, we use some augmentations which are catered to the client Aramco itself.
So they were asking, can you use the weather forecast for the fields? I don't believe a weather forecast was available at this remote location in the middle of the Middle East, but do you happen to remember, Himanshu?
No, Greg, I don't think any sensor outside of our system was not used because it was related to privacy and concern. So no external sensors were included in this project.
Yeah. Carl was asking, is there a second camera to improve a 3D or for training? So that's one of the things we did think about. If we have two cameras perpendicular looking at the flame, and then you could be more independent of which way the wind is blowing. Like if the wind is blowing straight towards camera A, camera B would be good at picking up at it. And so that was something we had thought of and proposed to the client, but they just wanted to stick with the cost of a single camera solution, at least at this phase. You know, for future rollouts, it may be something that we could bring up again and integrate between the two cameras. Is there any video card being used to boost performance? No, there was no, like you might consider an NVIDIA GPU or other video cards. For this particular solution, no. For some other solutions in oil and gas, we are, but not for this one. So other questions or comments?
There's something in the QA.
Oh, a QA. Okay, let me take a look at QA. Why does your client want to know the flow rate? How actionable are these flow rate results? So the client, before this project, they would have somebody sitting in a trailer in the hot desert that may be 120 degrees outside, looking to see if it's flaring or not. And so early on in the description of the project, as I was describing, they're doing a natural gas sweetening. They've got this chemical engineering process where they're removing the sulfur. But unlike a manufacturing line where you can stop the manufacturing line, like if there's a robot broken, you can shut down the manufacturing line and stop putting on wheels at station 1 and start putting on hubcaps at station 2. When you're doing chemical engineering, you can't necessarily stop chemical reactions. And so what's actionable about this is they get the notice earlier and they get sent out by email or SMS text messages, which can be to a group of people. And so as soon as a flaring starts, they can get alerted and to their messages, and then they can go investigate what is the problem in the chemical engineering process. So instead of having somebody who's sitting there watching, maybe on lunch break, get back a half hour later, then reports the flare, and they can report the flaring the minute it happens. The actionable part is that they can go into the plant and see what needs to be changed. Because the other thing about this chemical engineering process is everything is in enclosed pipes, enclosed tanks. you can't see it as much. And so you just have to look at dials and knobs and instrumentation. You know, if you're looking at a manufacturing car floor, you can see, is the factory running or are the cars stopped? And so it's much more of a trying to detect a symptom of an upstream problem. Back to where I was making the analogy, you know, if your car is burning black smoke, it's a symptom of your burning oil. And so you need to do some adjustments in your engine that you can't see inside the engine. So it's a similar kind of problem. It's like the first case where a symptom comes up. So that's one use case. The other use case is where flaring is happening. You know, how many hours of flaring are you getting per month or per year? And how can you reduce that? And so then if they can do some optimizations of their chemical engineering processing upstream to try and minimize the flaring, that's where the global warming impact improvement can be. So if they're trying some changes to their chemical engineering processes internally, and so if they can go from say 40 hours of flaring one month down to 30 hours the next month and 25 hours the month after that, that gives them feedback on how their systems are improving, and they're doing less flaring, they're doing less contribution to global warming at that site. So those are two types of actionable things from this. So that was a question from an anonymous attendee. But yes, a very good question. Other questions or comments? I see somebody had pasted in there. There was a link about another wind forecasting system for fires, but that would depend on having other sensors and knowing the terrain. The terrain in the desert was relatively flat, and there weren't other sensors. There wasn't other historical prediction because it was very much remote out in the wilderness. And so we wouldn't be able to use that system, but it would be good to look at to see if we could kind of improve at other sites where there are more wind sensors. So I do thank you for sharing that link. Okay. Well, if there's no other questions, are there any other ACM announcements or anything else anybody else wants to add to close? Okay, well, we can go ahead and close the meeting. Thank you for attending. We appreciate your good questions and thoughts.
Okay, thank you. I will end the meeting then. Thank you, Greg.
Okay, thank you.